track installation process, new steel rails are stacked on a special wagon running on existing tracks. Workers use dedicated lifting equipment mounted on the wagon to move each long rail from the stack to its installation position. The rails are carefully lifted and precisely placed onto the prepared rail bed, ensuring alignment with the existing track system. This efficient method allows continuous rail laying while minimizing manual handling. The gear manufacturing process at Klingelnberg follows lean production and lean management principles. Initially, gear designs are created and optimized using Chemo software. CNC turning and grinding machines are then employed to shape the components with high precision. Bevel gears are milled using the world's largest bevel gear cutting machine, the C300. After machining, parts are heat-treated in the in-house hardening shop with a monthly capacity of 140 tons. Ground bevel gears up to 1,100 millimeters are produced cost-effectively, with strict grinding burn tests to ensure quality. Surface crack inspection is performed using the magnetic particle method. Quality assurance is prioritized throughout the process, supported by contact pattern testing machines. A final inspection and customer acceptance take place directly at the facility, ensuring traceable quality. Finally, trained personnel manage optimized shipping to guarantee safe and timely delivery of the finished gears. In Altenmarkt, a team of highly qualified specialists designs and constructs machining centers and special-purpose machines. The process begins with dynamic simulations of machine components using finite element models during the development stage. These virtual tests guide the production of robust machine parts.
Weitere 480 Tonnen pro Monat sind direkt für Kunden Gramm und 3000 Kilogramm.
A key part of the operation is the in-house iron foundry. Here, iron castings are produced for column and pillar drilling machines, vertical boring mills, machining centers, and special-purpose machines. Around 120 tons of castings are manufactured monthly for in-house use, and an additional 480 tons are produced for external clients. The individual casting weights range from 100 grams to 3,000 kilograms. After casting, the components are primed, then passed through a painting and drying area for protective coating. The machined castings proceed to CNC machining on state-of-the-art equipment. Special tools, preset for component processing, are measured and adjusted. For larger and heavier parts, flexible machining cells are used. In one operation, a main spindle is turned. Another machine processes a bored head, which is later tested on a test bench.
Natürlich auch bei spanlosen Prozessen wie Fließbohren und Gewindeformen.
Once machined, components are grouped and stored. A feed module is inserted into a standard drilling machine, followed by the installation of the main spindle. Electrical functionality is tested, and the belt pulley and drive belt are installed on a programmable pillar drill. The V-belt system is then aligned and checked through a test run. This is followed by high-voltage testing to ensure safety and reliability.
1000 Kubikzentimeter pro Minute bei hochfestem Stahl. Anschließendes Konturfräsen mit einem hartmetallbestückten Messer.
Drilling machines undergo performance tests to determine their power curves during drilling and tapping, including non-cutting processes like flow drilling and thread forming. A computer-controlled vertical drill is shown performing high-speed milling using a carbide-equipped milling tool, reaching material removal rates of 1,000 cubic centimeters per minute in high-strength steel. A tool change is performed, followed by contour milling with a carbide milling head.
Testwerkstückes durch Abzeilung. Komplettbearbeitung von Ausklinkwerkstücken mittels einer frei programmierbaren Dreh-Schwenkeinrichtung.
The spindle head is mounted onto a special machine. The tool magazine disc is precisely adjusted for automatic tool changes, and the dual gripper test run is performed. A newly developed coordinate carriage is installed into the machine frame. Once the second sidewall is mounted, the power flow is closed. Energy supply chains are installed, and the twin tool magazine is tested again. The 3D processing of a test workpiece is performed using subtractive methods. Finally, complex components are milled, drilled, reamed, and sawed using freely programmable rotary swivel units. Free-form surfaces without digital data are scanned and transferred onto premium wood materials for reference. Machine enclosures are processed on a 6-station rotary transfer machine, and all functional checks are completed before final delivery. The forging process of steam turbine blades using 616 422 stainless steel begins with heating the electroslag remelted ingot to forging temperature in a high-capacity furnace. This heating ensures the material becomes plastic enough for deformation without cracking. Once the desired temperature is reached, the hot ingot is transferred to the forging press. The forging starts with billet forging, where the ingot is compressed between flat dies to reduce its cross-section and extend its length. This open die forging stage improves the internal grain structure and eliminates porosity. The workpiece is rotated and repositioned repeatedly to ensure uniform deformation along all axes. After achieving the desired billet dimensions, the billet is reheated and undergoes preform forging. In this stage, the billet is forged into a near-net shape, resembling the turbine blade, including the root and airfoil profile. Large hydraulic presses apply controlled force to shape the material gradually, maintaining optimal temperature to prevent defects. The forging dies may be flat or feature rough cavity shapes to guide the material flow effectively. Next, the preformed piece enters the precision forging stage. Using closed die forging techniques, detailed features of the blade, such as the dovetail, root fillet, and aerodynamic surfaces are accurately shaped. The material flow is carefully directed to fill the die cavity completely, producing components with superior dimensional accuracy and grain alignment. This step is critical in achieving the required mechanical performance for high-temperature turbine operation. Throughout the process, the workpiece may be reheated several times to retain forgeability and avoid thermal cracking. Skilled operators monitor temperature, alignment, and press parameters to ensure consistent quality. After the final forging operation, the part is slowly cooled under controlled conditions to minimize residual stresses. The result is a forged turbine blade with enhanced toughness, fatigue resistance, and strength ideal for demanding steam turbine environments. The manufacturing process at Carrier Wheels begins with the use of high-tensile and special-grade steel, selected based on application and customer requirements. The steel is decoiled and cut to length before undergoing shot blasting to remove mill scale and induce compressive stress. High-capacity flash butt welders are then used to join the rim components. Roll forming, horizontal flaring, and expanding up to 500 tons shape the rims into final profiles. In parallel, disc components are formed using presses up to 1,250 tons. Precision drilling and hub boring are performed by CNC multi-spindle machines. The assembly of rims and discs is carried out using automated CNC-controlled welding stations. Each finished wheel undergoes 100% inspection to ensure dimensional accuracy and quality. The wheels then move into a SCADA-controlled paint shop, where they undergo a 10-stage pre-treatment with zinc phosphating. Eco-friendly coating and a liquid top coat are applied in dust-free booths to ensure rust resistance and long-term durability. After final inspection, wheels are safely packed for delivery. All tooling is designed and manufactured in-house, and advanced CAD, CAM, and testing technologies are used throughout to ensure robust quality, product innovation, and cost-effective manufacturing. The heated steel billet is fed into the gap between two inclined, counter-rotating rolls of the Skew rolling mill. As it passes through, the billet undergoes plastic deformation and twisting, gradually forming a spherical shape. The finished steel balls then roll into a cooling water tank below. The installation process of lightweight flooring using light steel frame technology involves several clearly defined steps, each designed to ensure structural integrity, sound insulation, and flexibility in the finish. The process begins with the assembly of the lightweight steel structure, which serves as the main support for the flooring system. Vertical steel members and horizontal beams made from galvanized steel bars are installed according to the architectural drawings. These members are fixed together to form a sturdy and precise frame. The spacing and alignment of each member is carefully checked to ensure load distribution and dimensional accuracy. Once the structure is installed, EPDM acoustic strips are applied along the top of the horizontal members. These rubber-like strips are essential to minimize the transmission of noise and vibration between floors. They also provide a cushion between the steel frame and the floor panels. Next, the OSB3 panels are installed on the frame. These oriented strand boards are moisture-resistant and durable, making them ideal for structural flooring. The boards are cut to fit the grid, laid tightly together and screwed directly to the steel frame. This creates a flat, rigid base that can support heavy loads. After the OSB boards are installed, galvanized steel panels are placed on top of the wood. These provide additional stiffness and fire resistance. They are mechanically fastened to both the OSB and the underlying steel frame, creating a strong and lightweight composite flooring system. Finally, the selected floor finish is applied. This can include plywood, ceramic tiles, vinyl planks, or other materials, depending on the design requirements. The finish is secured with adhesives or locking systems. creating a clean and aesthetically pleasing surface. This method eliminates the need for heavy concrete slabs and reinforcing bars, reducing overall weight and construction time. The result is a high-performance flooring system that is lightweight, strong, acoustical, and adaptable to a wide range of finishes, suitable for residential, commercial, and modular buildings. The process begins by securing a circular metal blank onto a mandrel inside the CNC spinning lathe. Once properly clamped, the mandrel rotates at high speed. A forming roller controlled by the CNC system is then gradually pressed against the rotating metal. As the roller moves along a predefined path, it pushes the metal against the mandrel surface, causing it to stretch and conform to the desired frying pan shape. Throughout the process, the CNC system ensures consistent pressure, tool positioning, and forming speed, which helps achieve a smooth and symmetrical final contour. Once the metal is fully shaped, the machine stops, and the newly formed frying pan is removed from the mandrel. This precise and repeatable method ensures uniform wall thickness and dimensional accuracy, making it ideal for producing high-quality cookware efficiently and in large quantities. Steel cages for deep foundations are assembled by first bending spiral rings to the required diameter and shape according to the design. These rings are then laid out and aligned on a work platform. Next, longitudinal steel bars are placed inside the rings, running the entire length of the cage. Workers carefully tie the rings to the longitudinal bars at specified spacings with steel wire, ensuring proper alignment and spacing. The cage gradually takes on a cylindrical shape as more rings are added and secured. Once completed, the entire cage is inspected for straightness and structural integrity before being moved for installation. This manual process ensures the cage is structurally sound and ready to be placed in the drill shaft. The hot forming process of dished ends begins by placing a metal plate into a furnace, where it is heated uniformly to a high temperature above its recrystallization point. Once the required heat is achieved, the softened plate is transferred to a hydraulic press. There, it undergoes a pressing cycle where a die gradually forces the plate into a concave shape, forming the initial curvature. To achieve the desired profile, such as ellipsoidal or hemispherical, the plate may go through multiple pressing stages with intermediate reheating if necessary. Throughout the process, operators monitor the alignment and positioning to ensure symmetrical forming. After pressing, the dished end is removed and allowed to cool slowly to relieve internal stresses. In some cases, final shaping or trimming is performed to meet dimensional tolerances. This controlled hot forming process produces strong, precisely shaped dished ends, ideal for pressure vessels and industrial applications requiring high structural integrity. The manufacturing process of a Prolite carbon fiber wheel begins with the precise cutting of carbon sheets into designated segments. The rim structure is reinforced at the spoke hole areas using a 3K weave, providing added strength. Multiple layers of carbon are then carefully laid up, each calculated for optimal performance and durability. Heat is applied to soften the resin, allowing the carbon to be molded into the desired shape. Depending on whether the model is tubular or clincher, the tire bed foundation is formed accordingly. Successive layers are applied to build the sidewalls and outer face of the rim. These layers are smoothed and wrapped tightly to prevent slippage before the rim is inserted into a mold. The mold is heated gradually to allow the resin to flow. Then pressure is applied in 2 stages to eliminate excess resin and ensure compact layering. Prolite uses thick-wall silicon air bladders superior to standard poly bags, which allows molding at double the typical pressure, resulting in stronger and lighter rims. After molding, the rim is cleaned, degreased, and visually inspected. Decals are applied by hand, then baked in a low-temperature oven. A protective clear coat is added, followed by final curing in the oven. The completed rim is then transferred to the wheel building facility. In wheel assembly, nipples are pre-lubricated in heavy oil for smoother fitting. Spokes are installed using a custom tool tightened in 3 stages. Tensioning continues until optimal roundness, dish, and spoke stress are achieved. Hydraulic presses bed the spokes, and each wheel undergoes 6 cycles of truing and bedding in. Every wheel is inspected by a QC engineer and assigned a serial number, recording tension data and geometry. High-performance testing includes simulations on a machine nicknamed the Beast, which replicates extreme road conditions and load-bearing stress. Braking surfaces are also tested under repeated high-speed cycles and prolonged pressure to ensure durability. Wheels that pass all tests are road-tested in diverse terrain. Finally, each wheel is packaged with accessories and prepared for shipment to the customer. Gazi Metal, part of the Gazi Iglo family and a leading Turkish steel trader since 1927, has established a state-of-the-art cold rolling mill complex built by SMS Group. This facility enables the production of high-grade cold-rolled steel strips used in the automotive, domestic appliances, and silicon steel industries. The plant currently produces 350,000 tons annually, with strip widths ranging from 600 to 1,550 millimeters and thicknesses between 0.25 and 3.0 millimeters. Key components delivered by SMS include a semi-continuous pickling line with acid regeneration, a reversing cold mill, a skin pass mill, advanced drive systems, and complete electrical and automation solutions. The turbulence pickling system ensures efficient descaling with minimal acid use. Thanks to SMS's flexible expansion concept, the facility is designed to double its output and later reach up to 1 million tons annually. Future upgrades include continuous pickling, additional rolling mills, and tin plate production. This strategic investment positions Gazi Metal as a major player in flat steel production, with a focus on quality, sustainability, and market adaptability. Pepsi Bottling Ventures operates one of the most advanced water bottling systems in North America. At the Winston-Salem facility, a modern block bottling line is used to efficiently produce Aquafina water. This integrated system combines three key machines, blower, labeler, and filler, into a single block. This setup minimizes the need for conveyors, reduces container handling points, and enables pressureless conveyance, enhancing both hygiene and speed. Major advantage is that one operator can oversee the entire process, and if one labeling module fails, production continues using backup modules. The system includes accumulation zones that allow the filler to run continuously, even if the shrink wrapper stalls briefly. By manufacturing and labeling their own bottles, Pepsi Bottling Ventures achieves high efficiency and sustainability, reflecting its commitment to water conservation, technological innovation, and operational excellence. The production process begins with barcode-tracked raw materials stored in an intelligent warehouse. In the conductor section, high-quality stranding and cabling machines form Millikan conductors up to 3,500 square millimeters. Medium voltage cables undergo triple extrusion with nitrogen-protected CCV lines. High-voltage cables are manufactured vertically in a VCV tower to ensure quality, using 4 production lines and online monitors for insulation control. Smooth aluminum sheath cables are then applied, followed by PE outer sheathing. Finally, cables are tested in an accredited high-voltage lab. The process of manufacturing brass lamp heads begins with a solid disc of virgin brass mounted securely on the DMS Revolution CNC metal spinning lathe. The machine spins the workpiece at high speed, while a precision tool slowly presses into the brass. This causes the metal to flow axially along the mandrel's shape, transforming the flat blank into a smooth, rounded lamp cap geometry. During the spinning process, the CNC lathe applies consistent radial pressure, which thins and elongates the brass uniformly. This technique, known as metal spinning, allows the formation of complex curves without material waste. The tool path follows a programmed profile that ensures each contour matches the desired lamp design. Cooling fluid bathes the spinning piece to manage heat and preserve material integrity. Once the brass achieves its final shape, the CNC automatically stops. The technician removes the lamp cap and deburrs any minor edges by hand. The result is a beautifully symmetrical, polished brass cap, solid, seamless, and ready for final finishing. The process showcases how advanced CNC spinning turns a raw brass disc into a refined, functional lighting component with precision and elegance. The production of aluminum bottles begins with designing aluminum bottles in desired shape. Next is the process of an extrusion press, where an aluminum slug is forced through a die to form a cylindrical shape. This extrusion process defines the basic body of the bottle. Afterward, the bottle undergoes brush and trimming operations to smooth the surface and precisely cut the open end. The bottles are then transferred to the washing system to remove any oil, dust, or metal residues, ensuring a clean surface for the next stages. Following this, the internal coating process applies a protective layer inside the bottle to prevent chemical reactions between the contents and the metal. Next, base coating is performed on the exterior, providing a foundation for decorative layers. The painting stage follows, where bottles receive their final design and branding, often through multiple layers of ink and curing cycles. After painting, the necking machine reduces the diameter of the bottle's opening through a series of forming stages, creating the desired contour for the cap area. Once necking is complete, threading is applied to the top, allowing for secure closure compatibility. Finally, in some production lines, the bottle is filled with the intended product immediately after threading, ensuring cleanliness and efficiency in the bottling process. Each stage is precisely controlled to ensure uniformity, durability, and a premium finish.